Hi, my name is Micah, and working with Arav, Kitty, and Shreyas, we are a team of 4 CMU BME master students working in collaboration with the Colloidal Analysis and Research Lab, or CAR Lab, from the University of Pittsburgh. It is this collaboration that enables our research to be possible. Age-related macular degeneration, or AMD, is one of the leading causes of vision loss and even blindness, affecting over 200 million people globally. An example of AMD is in the visual depicted on the right. Now, AMD primarily affects the fovea. This is that small back part of the eye responsible for central sharp vision. Importantly, the fovea is not a single point, and anatomically, it's better represented as an area. Now, it's really hard to localize the fovea with diseased eyes. On the left, it's pretty easy to determine where the fovea might be for a healthy en-face OCT eye, but for more advanced pathological cases, it can be difficult to determine where the fovea might reside. Now, to understand our research, you need to understand an ETDRS map, or grid. These basically capture where light focuses in your retina over the macula, and they're intended to measure retinal thickness. Clinicians rely on these grids to basically evaluate the macula. And the common assumption about them is that this fixation point in the center corresponds to around where the foveal center would be, or where the fovea is in general. But this assumption is not always valid, especially in the cases of more advanced pathologies. And here we have a problem. If the ETDRS fixation point does not align with the fovea, retinal thickness values become misleading. Thus, our team had the following objective. Our team wanted to determine how well OCT-based anatomical estimates of the fovea across different stages of AMD align with these ETDRS fixation centers. To understand our research, we need to understand the difference between B scans and en-face OCT. B scans are basically a side view of the retina, and they're basically like the depth and the layers. They're very, very information rich, and with a complete set of them, you can completely convert them into an en-face OCT, which are something more like a bird's eye of the retina. And they contain less information compared to B scans. Because B scans are so rich in that retinal thickness information, our team started from pure B scans to ensure anatomical accuracy. Now, in step 1 of our deep learning pipeline, our team first started with a set of B scans and tried to map them to create an estimate for foveal area. In step 2, with these estimates, our team tried to go from a raw en-face image, which is what clinicians more often see, and get a segmented area. In step 1, the way that we were able to get an area mapping from a set of B scans was we first had to determine which of these B scans contained a fovea in the first place. To do that, we had to train a classification model. We fine-tuned VGG16 and achieved a validation accuracy of almost 99% in classifying whether it had a fovea or whether it didn't have a fovea. Once we were able to isolate which of these B-scan slices had a fovea, we could then apply a heat map saliency to them to determine whether where the features relevant to locating the fovea were located. From these features, we could then map and determine where on the raw en-face image the foveal area would be located. We actually tried many different methods for heat map saliency and determined the occlusion mask was the most effective. This is because for occlusion mask specifically, there was a high concentration of saliency around the area of the fovea. This is what our mapping process looked like. Our next step was going from an unlabeled en-face OCT image to a labeled one. This involved training a deep learning model that was structured with a vision transformer-based mask autoencoder and followed up with a UNet++ decoder. These are some of our results. And these are some of our results from our initial model. And after our initial model, our team then trained on pathological cases for greater robustness. Our team was fairly happy with our initial model results because they had fairly strong alignment between the occlusions mask and the model results. Once our team completed our deep learning pipeline, we were then ready to move to our final step, comparing our predicted area to these ETDRS grids. Before we did that, we had to do some post-processing, but we really wanted to answer this question: do these predicted areas align with the ETDRS grids? Now, an important side note that when we were comparing our fovea area, we realized it was more convenient to think of ETDRS not as a single point, but as an area. The reason behind this is our goal was to determine alignment between the fovea, which was inherently an area. And so we actually ended up being beneficial to turn ETDRS into an area, which is a better comparison for area alignment. Now, here are some of our results and conclusions. Our analysis revealed that between estimated foveal areas and the ETDRS central area was generally preserved in early AMD, but it progressively declined as given increasing disease severity. Furthermore, ETDRS fixation centers, we concluded, are a reasonable gold standard for localizing the fovea in OCT-based retinal thickness analysis in healthy and early AMD. But they become unreliable in intermediate and late disease cases, for example, in the case of geographic atrophy. Ultimately, our estimated foveal areas will be used as a key parameter in the CAR Lab's algorithm for generating de novo ETDRS maps. These estimates will help clinicians monitor changes over time in retinal thickness and assess whether it worsens with treatment for patients with normal or early AMD. Thank you so much, and here are our references.